Okay, so this is the Zoom meeting for Physics 231C, first day of December. So here we are. Exam 3 was earlier this week, and the corrections exam should have been already done. And the final two chapters for the semester are chapters 13 and 14. Thirteen is heat, 14 is thermodynamics. There'll be a reading quiz, which is due next Monday, and which covers both chapters. And there'll be a problem set, which is due Friday next week, the last Friday of the semester, which will be on both of the chapters. Another thing you have to do in the final week of classes is the post-test. You think back to the first week of classes, you had a pre-test, and the last week of classes, you have the post-test. That's important for your final grade because that'll provide a maximum number of points corresponding to 1% of their final grade. So that's kind of important to do. I think it's timed 70 minutes long. It is a 70-minute time limit. So sometime when you have 70 minutes free with no interference, do the post-test. You don't have to study for it. You just do it in 70 minutes. It'll be due, I guess that's Wednesday next week, but it'll be open, I think, on Monday. So it'll open up Monday. You have Monday, Tuesday, all day Wednesday when you can do it. You just have to make sure you have a 70-minute period to work on it, because you can't, it's timed. You can't turn off the timer. And then we have final exam week. And for this class, Physics 231C, the final exam is at the end of final exam week. It's Thursday night. All right, so let's take a look in this Zoom meeting at some of the topics in chapters 13 and 14. They also depend a lot on the topics you studied before in chapter 12 on temperature. So here's a summary, a quick summary of chapter 12. Defines temperature and various temperature scales, thermal expansion, ideal gases. The ideal gas law is going to be important in the last two chapters. The kinetic theory of gases. Maxwell and Boltzmann worked out the distribution of velocities in an ideal gas at a temperature T. So the speed distribution is kind of complicated, but it's proportional to v squared, and then an exponential of minus v squared times a constant, which depends on the temperature. So you've already seen this a little bit on the chapter 12 homework and exam 3. Now here's a summary of chapter 13, which is on heat. First of all, what is heat? Well, here's what the authors of the textbook say. Heat is energy in transit. In other words, heat is a kind of energy transfer. There are really two kinds of energy transfer. One is by work, and one is by heat. And heat is energy transfer on the atomic scale. So it's energy transfer to atoms or molecules. making up some material in a system. The unit of heat is joule. It's kind of energy transfer, so it has the same unit as joule. But in chemistry, they often use the unit calorie. And 1 calorie is a little bit more than 4 joules. A food calorie is 1,000 calories. A food calorie is also called 1 calorie, but it's actually 1 kilocalorie in terms of chemical calories. Now, relating heat and temperature, heat flows when there's a temperature difference. And the relation is proportionality. The amount of heat that flows when 2 objects with different temperatures are in contact will be proportional to the difference in temperatures. The constant of proportionality is called the heat capacity or the specific heat. The specific heat is the heat capacity divided by the mass of the samples. Now, in the case of gases, the heat capacity is the number of moles, that's N, times a constant, which is called the specific heat per mole. You may have studied heat before in a chemistry class. That was chapter 13. This is also chapter 13, so this is wrong. This is also chapter 13. Another case where heat occurs is when there's a change of phase. For example, think of water. Water has 3 phases: solid, liquid, and gas. When the sample of molecules changes from one phase to another, it absorbs heat at a constant temperature. So, for example, when you boil water, the water and the water vapor are both at the boiling point, 100 degrees Celsius. And as you boil the water, the liquid water, the temperature remains constant, but you're adding heat. So phase changes have transfer of energy. You're transferring energy to the molecules in the liquid. You're giving them more energy so that they will escape from the liquid. And we define heat of fusion and heat of vaporization. So these various constants, like the specific heat, the heat capacity, the heat of vaporization, heat of fusion, those constants you can look up in tables, some tables in the book. There are different kinds of transfer of heat. There's conduction, convection, and radiation. So heat can be transferred in electromagnetic waves. That's called radiation. Well, you're going to need all of those equations from chapter 13 for the homework assignment. Now, I'll go over a few hints for problems in the homework assignment. That's the homework assignment, which is due a week from today, December 8th, the last day of classes. It's a rather long assignment because it covers 2 chapters. That'll cover both chapter 13 and chapter 14. So here are some of the problems that are in that homework assignment. For example, there's a problem called 2 metal objects. You have 2 metal objects at different temperatures. They're in contact. then there'll be heat transferred from the hotter material to the colder material. But energy is conserved, and heat is energy transfer, as I said a minute ago. So the amount of energy transferred from the hot object will be exactly the same as the amount of energy absorbed by the cold object. Now, the relation between heat and temperature has to do with the specific heat. Heat capacity is the mass of the object times the specific heat. So here's the amount of heat transferred from the hot object. Here's the amount of heat transferred to the cold object. They have to be equal but opposite so that energy is conserved. And so in this problem, two metal objects, you're probably told something like the masses, and you have to analyze the changes of temperature. How do the temperatures, you have some initial temperatures. What are the final temperatures? You can look at figure 13.5 to understand this equation. Or there's another problem in the assignment called three liquids. Well, that's just the same as two metal objects, only now there are three of them. So you'll have to have multiple equations of this type, and you have algebra to do to solve for the unknowns. I'm not quite sure what this problem is, but there's probably an assigned problem called speeding water. There's a problem called bag of lead shots. You drop a bag of lead shots from some height h. Well, at that height h, it has a certain potential energy, mgh. Now you drop it and it lands on the ground, comes to rest. It no longer has that gravitational potential energy, but energy is conserved. That's the important property of energy. So where did the energy go? It didn't do any work. It was transferred by heating from the friction involved in the lead shots. So there'll be an equal amount of heat transferred to the bag of lead shots. That will raise its temperature a little bit by the equation that the energy transfer is the mass times the specific heat times the change in temperature. These hints, by the way, are also published on the supplemental content as the hints for chapter 13. Here's an example, converting ice to water. So you have a block of ice, big ice cube. You heat it up with a flame or something. It'll melt. You'll end up with a glass of water, liquid water. And the question is, how much heat was absorbed from the flame to convert the ice into water? And again, you can use specific heats and temperatures. There'll be a specific heat for the heat absorbed by the ice. There'll also be a specific heat for the heat absorbed by the liquid water. There'll also be heat absorbed for the phase change. So this will involve the heat capacity of ice, or the specific heat of ice, the specific heat of liquid water, which is a little bit different, the changes in temperature of the ice, the changes of temperature of the liquid water, plus the heat added to convert solid to liquid. You have to give those molecules extra energy to cause them to come out of their crystalline positions and make a liquid. So that will depend on the latent heat of fusion. Here's a problem about a steam pipe. I don't know if that one's assigned. Here's the power emitted by a hole in the wall of an oven. Suppose you have an oven at a temperature T and you drill a little hole in the oven. Well, then there'll be black body radiation coming out of that hole. The equation for black body radiation is called the Stefan-Boltzmann law. It's equation 8. The amount of power per unit area escaping from the inside of the oven in electromagnetic radiation is given by a constant, sigma, times the temperature to the power 4, sigma T to the 4th. That's the Stefan-Boltzmann law. You may also need to know Wien's constant to do this problem. I'm not sure whether you need to know Wien's constant to do this problem. You certainly need to know Stefan's constant. Sigma T to the 4th. That unit might be wrong. I think it's watts per meter squared divided by degree Kelvin to the 4th. So when you multiply it by the temperature to the 4th, that'll give you watts per square meter. So I think this has to be divided by meters squared, I think. Anyway, look up equation 13.8. Now you might also need to know Wien's constant. So that's really a topic in Physics 232, but you can look it up and do a Google search on Wien's constant and you'll find out how to use that. There's a problem about power radiated by the human body. You know, your temperature is 98.6 degrees Fahrenheit. Room temperature is about 70 degrees Fahrenheit. So you are hotter than the air in the room. Well, when two materials are at a different temperature, there'll be an energy transfer from the hotter object to the colder object. So you will be transferring energy to the air in the room. A good portion of that is by electromagnetic radiation. It's infrared electromagnetic waves. So there's an example in a chapter, example 13 in chapter 13, which describes human radiation as an example of energy transfer or heat. In that case, it's heat of radiation. All right, so that's chapter 13, heat, all about heat. And you know, the important equations are in the summary. Well, that was chapter 12. Chapter 13, you need to understand the units, understand that heat is a kind of energy, or rather an energy transfer. Heat capacity and specific heat. Heat capacity is just the total amount of heat capacity, but specific heat is the heat capacity for a given amount of material. Could be heat capacity per kilogram, or heat capacity per mole in the case of a gas. And then there's also a kind of heat associated with phase changes. And then there are really 3 different kinds of energy transfer in the form of heat: conduction, convection, and radiation. And there are some equations you need to know for that. So that's chapter 13. It's a rather limited set of topics. It's about how heat and temperature are related to each other. Now let me go on to chapter 14. 14 is more theoretical and a kind of a more involved subject called thermodynamics. How does this energy transfer occur in different ways? So you have to read chapter 14, and there'll be several sections, each of which corresponds to a different kind of process, which involves heat. So some of these processes involve gases. And so one example is compression or expansion of a gas. A gas, the ideal gas law already from chapter 12, pressure times volume is number of moles times R, the universal constant, times T. So it relates pressure, volume, amount, number of moles, and temperature. Well, when there's compression, the volume changes. Okay, so the volume changes. So that means pressure and temperature must change, because pressure times volume is nRT. N is constant if you don't change the amount of gas. So it must be changes in temperature and pressure. Well, there are different ways in which this change can occur. One is called isothermal. In an isothermal compression, the temperature doesn't change. The volume does change, and therefore there's a corresponding change in the pressure. Since the temperature doesn't change, pressure times volume remains constant. So if the volume is compressed by a factor of 2, the pressure increases by a factor of 2. So here's a problem from the homework assignment due a week from today. You have hydrogen gas at a certain temperature and pressure, and then it is isothermally compressed. The pressure increases. What's the change in the volume? So you use the ideal gas. Well, here are some hints. You use the ideal gas law, and then you suppose that one of the parameters in the ideal gas law changes. In this case, pressure changes. Then other quantities in the equation have to change correspondingly. But since it's isothermal, the temperature doesn't change. All right, so here are the hints. Again, these hints are in the hints folder for chapter 14. So if you try to do the problem without the hints, read the chapter, try to do the problem without using the hints. If you don't quite see how to do it, you can take a peek at the hints and then go back and try to do the problem again after you've seen the hints. Here are some of the hints. Or there's another example from the homework assignment. A heat engine. A heat engine is a device that, by expanding and contracting some kind of fluid like a gas, will do work and absorb or emit heat. So in this problem, an ideal heat engine absorbs 87 kilojoules of heat. So that's the total energy transferred in the form of heat, and exhausts 67 kilojoules of heat. So it takes some heat in one part of its cycle, and then it exhausts some heat out to the environment in another part of its cycle. The question is, what's the efficiency of the engine? That's a measure of how much work did it do. So efficiency is the amount of work that you get out that's useful to you, divided by the amount of heat that you put in. So you're paying to add heat to the system. An engine does cycles. An engine is a cyclic process of some sort. So it's a cyclic process. And in part of this cycle, you're adding heat. In part of the cycle, you're losing heat and doing work. Well, work is what you want. The heat you put in is what you pay for. Now, the heat that's exhausted to the environment is just useless, but it's a necessary part of the cycle because of the conservation of energy. So, efficiency is the amount of good stuff you get out, that's work, divided by the stuff you have to pay for. That's the heat that you add. The ratio of those two is the efficiency. So, it's like any physics problem. To do the problem, here you have this problem. What are you going to do? First, draw a picture. It says it's an ideal heat engine. That's also called a Carnot engine. That means the cycle that it undergoes involves an isothermal expansion and an adiabatic expansion. This is again described in chapter 14. Also, the efficiency of heat engines is part of that description of the Carnot cycle. So here's a picture. You want to draw a picture of the problem. You have a cold region. You have a hot region. That's a heat engine. You're going to pay to add heat to the fluid. From the hot side, it'll be added to the fluid. Then part of that energy will come out as work. That's what you want. And part of it will just be lost into the environment or into the cold part of the system. So there's a kind of picture of a heat engine. So, study this. Figure 11 shows energy flows in a heat engine. There are actually three energy flows. There's heat that flows into the engine. There's heat that flows out of the engine. There's also work done by the engine. By conservation of energy, the heat in is equal to the sum of the heat out plus the work. That gives you one equation. You need to know more than that in order to solve the problem. You need to know, how much heat is there for a given change in temperature. And that depends on whether it's a isothermal or adiabatic change in the fluid. So here's another figure you need to look at. Figure 12 shows the pressure volume diagram for a Carnot cycle. So if we think of going around this cycle again and again and again, each time you complete the cycle, you get a certain amount of work out. There's an adiabatic compression followed by an isothermal expansion, followed by an adiabatic expansion, followed by an isothermal compression. So you see how the volume is decreasing, then increasing some more, then decreasing back to where it started from because it's a cycle. Since it's a cycle, it starts at D and it ends at D, or I could say it starts at A. It first undergoes an isothermal expansion, then an adiabatic expansion, then an isothermal compression, and then an adiabatic compression. So come back to the same volume, VA. but it's increased and increased and decreased and decreased to come back to the same point in the cycle. Now, the change in pressure for these different kinds of changes in the system, there's a change in pressure. There's a different formula for isothermal expansion and adiabatic expansion. So how does the pressure change? Well, it starts by pressure decreases, then the pressure decreases some more, then the pressure increases a little bit, then it increases even more. So it's a cycle where there are changes in pressure and volume. Sometimes the temperature is constant at the high temperature. Sometimes the temperature is constant at the low temperature. So those are the isothermal changes. And during the adiabatic changes, the temperature is not constant. So the temperature of the fluid inside the cycle is going up and then going down again. It comes back to the starting point. Anyway, this is analyzed in the section on the Carnot cycle, and there's a formula for efficiency of the heat engine. Here's another problem involving a heat engine. A heat engine is to be used where the environmental temperature is 10 degrees Celsius. Now you have to have a hot reservoir at a higher temperature than 10 degrees Celsius. And the question is, if you want 40.5% efficiency, how hot does the hot reservoir have to be? You have to add heat. You have to keep the temperature of the hot reservoir constant. And that means to say you have to add heat to the system. So that's costing you money. You have to burn something. But you're getting work out. And the work over the energy put in, that's the efficiency. So this is again an ideal heat engine. So see the equations on about page 300. You can also run the cycle in the other order. You can run the cycle backwards. If you take a heat engine and run the cycle forwards, you get work out. You put heat in and you get work out. But if you run the cycle in the other direction, you have to put work in and you get heat out. Well, that's what a refrigerator does. You add work. So your refrigerator in your kitchen has a motor in it, an electric motor. It's plugged into the wall someplace. And that electric motor is putting work in to the fluid in the heat engine. So you're adding work, but you're taking away heat. And that leaves the inside of the refrigerator colder because you've taken heat away from it. If you take heat away, the temperature will decrease. So purpose of your refrigerator in your kitchen is to heat up your kitchen using heat in the inside of your refrigerator, making the inside of your refrigerator cold. But in order to get the heat out from the cold inside of the refrigerator, you have to do work on it. So you have to pay someplace. You have to pay for the electricity used in the motor. Now, the efficiency in the case of a refrigerator is not called efficiency, it's called coefficient of performance. So again, you can read about refrigerators and how to calculate the coefficient of performance. Say a refrigerator adds work, 185 joules each cycle, removes heat, say 530 joules each cycle, that keeps its interior at a cold temperature. What's the coefficient of performance? All right, so that's, again, in pages 300 and a little after page 300. Here's a kind of a diagram of the refrigerator in your kitchen. The inside is cold. Outside, there's a motor which compresses the gas. So electrical energy is used to compress the coolant. And then it has to be a cycle, so you have to have an expansion valve to go back to the same point in the cycle. And on this side, you'll take heat away, leaving the inside at a cold temperature. All right, so let's see, what else do I have here? A heat engine called a Stirling engine. Stirling engine is not a Carnot cycle. It's a different cycle, but it's, again, a heat engine uses a heat pump. So a heat pump is like a refrigerator. You put work in, you get heat out. You can use that heat to heat up your house during the winter. And that's called a heat pump. The device is pumping heat into your house, taken from work that's used to run the engine. All right, so there's a high temperature and a low temperature. There's, in the problem, it gives you the high temperature, it gives you the low temperature. Again, the coefficient of performance will be what you get out, that's heat, versus what you put in, that's work. Let's see, here's the hint for doing this problem. First, draw a picture. Okay, draw a picture. Sort of draw a picture like this, like a refrigerator, or like this. Here you'll have temperature from the outside, and work will give you temperature on the inside. So it'll be this same kind of arrows, but the arrows going in the opposite direction. So draw a picture, label it with the amount of work, the amount of heat, actually two kinds of heat taken from the hot side or put into the cold side. The Stirling engine is not explained in the textbook. So do some research, do a Google search on Stirling engine to make sure you really understand what the diagram shows. Stirling was a Scottish inventor of the early part of the 19th century. And he figured out how to make a heat engine, not for the purpose of running, Scotland was famous for its steam engines. James Watt was another Scotsman. Well, okay, so you can use a steam engine to drive a railroad train or a railroad locomotive, or to drive a ship. That's getting work out of the engine. But if you turn it around backwards, if you run the cycle in the other direction, you can use it as a source of heat. And that's called a heat pump. You're pumping heat from outside to inside. This is for heating your house during the winter. It's cold outside. You want it to be warm inside. So you want to pump some heat from the outside. That's energy in the molecules of the atmosphere outdoors. You want to take some of that energy and bring it indoors to keep the temperature of the molecules indoors higher. Well, it won't happen naturally. I mean, naturally, heat flows from a high temperature to a low temperature, not vice versa. But if you add work to conserve the energy, then you can pump thermal energy from a cold region to a hot region. And that's a heat pump. You're pumping heat around. All right, here's a kind of picture you would draw. Here's energy flows in a heat pump. You know, that earlier picture was energy flows in a heat engine. So this is a heat engine where you put heat in and you get work out. And you also must have some heat going out. So you cannot convert all of the heat into work. You can only convert some of the heat into work. The rest of the heat, it's energy conserved, the rest of the heat goes back out to the environment. All right, so the heat flow in a heat engine is from the hot side to the cold side. But now here's another picture which shows the heat flows in a heat pump. Now here you are pumping heat from the cold region into the hot region. So it's cold outdoors in the winter. You want to keep it warm inside. So you want to pump heat, or you want to pump molecular energy, I should say, from the outdoors to the indoors. But energy is conserved, so you can't get it all. You have to add something. You have to add what you have to pay for, work, to run the heat pump. So a heat pump uses energy W to extract heat QC from the outside and deposit a greater amount of heat QH to the inside. And by conservation of energy, QH, that's what you want, is the work you put in plus some heat from the outdoors. All right, so now at the end of problem set 11, there are also some problems related to chapters 13 and 14, which will be a good way to study for the final exam. The final exam is going to include questions from the whole semester, but there'll be a bunch of questions from chapters 13 and 14, which we haven't had on any of the previous exams. So to study a little more for the final exam, try these problems, which are given in problem set 11. Try these problems. And that'll be a way to study for the exam. Since these are study problems, they're not worth points on the homework. They're just for study purposes. So do these problems. You can find out if you got the right answer by using log kappa, but you won't get points for those problems. Now here's a kind of a grand overview of the whole semester. You know, we started in the beginning with mechanics, motion. So that's motion in one dimension, motion in two dimensions, chapters 2 and 3. Here are some of the possible exam questions. Constant acceleration, projectiles, circular motion. You remember these from earlier in the semester. Oh, and chapter 4 on forces. Newton's laws, free body diagrams. So, you know, this is the earliest part of the semester. After chapter 4, we had the first exam. Then we went into energy, momentum, oscillations, and rotations. That's chapters 5 through 8. Here are some of the topics in those chapters, which could be put on the final exam. Then we had the second exam. After the second exam, we had the third exam, which included gravity, solids and liquids, sound, temperature. That's exam 3 that we just finished earlier this week. here are some of the topics that could be put on the final exam. And then finally, the last two chapters, heat and thermodynamics. What kind of things might be put on the final exam? So you should use this table to prepare yourself for the exam. What should you study? Well, study your notes. The main thing is to study your notes that you kept in your notebook. But, make sure that you understand all of these concepts which could be put on the exam. You don't really have time to write down this table, so I'll publish this Zoom meeting, and you can also look up the notes on the supplemental content, and you can look at this table of exam topics. They'll be in the folder in supplemental content called Zoom meeting notes.